Okay, so actually, I think last time you had missed a lecture. So we went through task and
Mm,
functions. Um,
okay.
Task and functions are two kinds of subroutines in Verilog,
Mm-hmm.
where if you've done any other programming in any other language, especially C language, you might have heard about functions and subroutines, which are
Yes.
basically small programs or small subsections of the programs which can be defined separately and called separately on a repeated basis if required. So
Yeah.
similarly, we have tasks and functions in Verilog. Uh, just for
Mm-hmm.
your benefit, let me just quickly recap that and then you can just move forward, I guess.
Okay. Thank you.
Yeah, so if you look at this, there are obviously some differences the way a task work and a function works. Functions has certain limitations. Task really doesn't have any limitation. Function can enable or it can call any other function, but not a task. So a function can only call another function, but not a task. It has to execute in zero simulation time. We cannot have any delay statements inside the function. So it has to always execute in zero simulation time. And no other timing control statements are allowed inside a function. So like for example at pause age clock or at neg age clock or anything of that sort, any timing control statements are not allowed in a function. A function needs to have at least one input. It can have more than one, but at least one input is required, and it will always return a single output, not more than one output. Only a single output will be returned back from it. That's how a function works. For a task, there are no limitations. We can call another task or we can call another functions from within a task. It may execute in non-zero simulation time. So you can have delay statements inside a task, or you can have timing control statements inside a task, waiting for a passage of clock or a neckage of clock, for example. It may have any arbitrary numbers of inputs, outputs, and in-outs bidirectional ports. So it can have 0, 1, or multiple input ports, or 0, 1, or multiple output ports, or the same goes with in-out ports. It doesn't have to return any value. If it is so, if there is an output port, it will return some value. If there is no output port, it will not return. There are no limitations per se on a task. The kind of
Mm-hmm.
limitations we see on a for a function, this thing description.
Yeah.
But there are certain common things that are applicable for a task and a function. Both task and functions are defined inside a module. It's inside the module, just like a always block is inside a module, and they are local to the module. A task and a function can have its own local variables, which is registers, but not nets. So we can declare registers inside a function or a task, and it can have its own events. So functions cannot have events. Tasks can have an event like at passage of clock. It becomes a clock event. It contains only behavioral statement. Inside the task or a function, I cannot instantiate some other module. The instantiations of other modules are possible at a module level, but not inside a task or inside a function. Task and functions do not contain initial or always statements, but the other way around is allowed. Initial block or always block can call a function or a task. Okay, any questions?
Yeah. No.
Yeah. So can we go? Do you want to note this down, or do you want? Can we go forward?
Um, I'll get a recording of this, right? Then I'll.
Yeah, yeah. I'm recording
Yeah.
this, so you can get a hold of that recording.
Okay. Yeah. Sweet. Yeah, we can move on.
Okay. Then so there are some. I can just show you a couple of examples for a task and a function, the way they are called. Yeah, so this is an example of a task. Module operation. A module doesn't have any particular input output ports. It's an empty port list. There is a parameter called delay, value 10. Capital A, capital B, each of them is a register 16 bits. Capital AB and AB or AB XOR are three registers, each of them is 16 bits. Now we are declaring a task called bitwise operation. Task bitwise operation has few outputs and few inputs. Small AB and small AB or small AB XOR, each of them is output 16 bits. Small a and small b are inputs, each of them 16 bits. If you remember, Verilog is a case sensitive language. That means the capital
Mm-hmm.
case labels and the small case labels will be different. Will be treated
Mm-hmm.
as different signals. Technically
Yeah.
speaking, you should not do this with the same name. You should try some other names, but this is just for understanding that capital A will be separate than small a.
Mm-hmm.
So these inputs and outputs are local to the task. Begin the task. Delay is a parameter which is declared at a module level. So it can be accessed from within the task. Hash delay AB and is equal to A and B. A and B are inputs. So we are going to logically AND them. It will be the result will be assigned to small AB and after this delay of 10 time units, whatever the time units are.
Mm-hmm.
AB OR is equal to A logically ORing with B. So we logically OR A and B inputs and the result will go to AB OR. AB XOR will be A cap. Cap is a XOR sign. So A and B inputs will be logically XOR. The result will go to AB XOR. Each of this is output. AB and AB OR and AB XOR are outputs from the task. End task. Then in the initial block, then we have an initial block where A capital A and capital B are initialized to certain values. 16 tick H, so it's a 16-bit hex value, hexadecimal value, 0000. B is initialized to 16 tick H 0001. So A and B are initialized to 0 and 1 respectively. And the initial block. Always at A or B. So A or B is part of the sensitivity list for always block. Any change in capital A signal or capital B signal, the always block is triggered for execution. Begin
Mm-hmm.
the always block. Inside the always block, I'm going to call this particular task. So since I'm calling the task, I have to map, these are called the arguments of the task. So I have to pass certain arguments. First three are outputs, second two are the other two, the last two are inputs. So the first three outputs will be mapped to capital and capital AB and capital AB or capital AB XOR, which is declared as registers at module level. And the inputs capital A and capital B will be mapped to the register capital A and B. So this A and B, capital A and B goes in as input, get mapped to the local small a and B. Based on this logic, the outputs are calculated, they come back here and get mapped to this capital sequence. So capital AB and AB or AB XOR will give me my result coming from the task.
Okay.
And the always block and end module. Any questions how this
Um,
works?
Not on how it works, but for the when you're calling the bitwise task,
Mhm.
does that is there a syntax for it that you have to give the outputs first and then the inputs, or
The only thing is, whichever order that you are declaring it within the task, you have to pass the arguments based on that. So if your input is declared
okay,
first, then A and B will go first, and
okay,
outputs, if they're declared last, then the outputs will get mapped to this.
okay,
So it's not like we don't have the concept of port mapping here, where the local formal and actual concept dot the signal port name and in bracket the local signal name. We don't have that
mm-hmm.
we use for other module instantiations. Here it's just like a regular. If you use C language functions, you just pass the arguments in the same order as uh, the inputs and outputs that are declared at the function level inside the function.
Okay,
So you have to know this since you have declared a task here, you know which are outputs first, outputs, then map outputs first, then inputs, or the other way around.
yep,
Okay, so this is there is another yeah, example of task. In this particular case, there is a input. There is a module called sequence, no input output ports. There is a reg called clock. Now this task, there are two tasks declared. You can have more than one task in a module. This task have zero input and zero outputs, both of them. And in the init sequence task, clock is assigned a zero value in the asymmetric sequence task. There is a clock generation that's happening. After 12 time units, clock is 0. After another 5 time units, clock is 1. Another 3 time units, clock is 0. Another 10 time units, clock is 1. So clock is, we are generating a asymmetric clock signal inside this task, which has no inputs and no outputs. And then in the initial block, I'm calling the init sequence, which will just initialize the clock range. In the always block, I'm calling the asymmetric sequence, in which the asymmetric clock will be generated. Again, both tasks have zero inputs and zero. Any questions
Yep.
on this?
No.
Okay. Let's look at functions. So functions have certain this thing, the limitations. So we'll see how it looks like. First thing you have to understand is function, implicit reg will be declared inside the function with the same name. Just show you example, it will be clear here. So in this is an example of a function, module parity m. ADDR is a register 32 bits declared at a module level and it is initialized to 0. 32-bit or 32-bit hex value or 32-bit binary value 00, all zeros. Reg parity is a single bit register. Now we are declaring a function called calculate parity. Now in this particular case, function, the rules for functions are it has to have at least one input. It will always have one output, only one output. What is the output? The name of the function itself is the output. And that function, the name of that function, internally a register will be automatically declared for that function name. I don't have to declare a separate range call or a separate register called calculate parity. When I call this function called calculate parity, that register is automatically declared inside the function. So for this function, there is one input which is called address and it is 32 bits. And there will be one output called the name of the function, calculate parity in this case. Begin, calculate parity is equal to cap address. So what is this? This is a unary reduction operator performing XOR logic. So address is the input, which is 32 bits. I'm performing a unary reduction operator on address input using XOR logic. That means 31st bit will be XORed with 38 bit. Then the result will be XORed with 29 bit. Then the result will be XORed with 28 bit, all the way down to 0 bit. It will get calculated, and finally we'll have a single bit value as a result.
Mhm.
That single bit value will get assigned to calculate parity, which is the output of the function. If you remember when we saw XOR logic can perform parity generation, parity calculations, because the truth table for a XOR gate, if you remember, if both inputs are same, output is 0. If both inputs are different, then output is 1. So 0
Mhm.
0 input, output is 0. 0 1 and 1 0 inputs, output is 1. Both inputs are 1 1, output is 0.
Yeah.
So that means if the inputs are different, output is 1. That means we are calculating OR parity.
Mhm.
Parity is the number of ones in a given data. Here we have 32 bits of data inside the function.
Mhm.
So this 32 bits of data, we are going to calculate the odd parity for it using the unary reduction operator using XOR logic. Inside the always block. So now this is end and end function. Always add address. ADDR is a register declared at module level. That's my sensitivity list. Begin the always block. Parity is equal to calculate parity ADDR. So ADDR, we are calling the function calculate parity inside the always block, passing this argument as ADDR, which will then internally get mapped to the address value inside the function. It will calculate the parity, send back the 1 or 0 value, single bit value. That single bit value will then get assigned to parity, which is a reg declared at the module. So parity reg will have my result for odd parity. If it is 0, that means we are having a even parity in for the 32 bits. If it is 1, that means the number of bits number of ones in this 32-bit are odd. If it is odd parity, the result will be 1. If it is even parity, the result will be 0.
Yeah.
Okay, so that's how this works. Then dollar display, it's anything with a dollar sign is called a system task, which we're going to see, I think, today. So we'll see how this is done. But this is like, have you done C language programming before?
Yes.
So you might have used a printf statement there, right? To print a message
Yes.
on the console. So dollar display is something like a printf statement. You can display the value of reg parity in this using percent %b means percent %b stands for binary format. So parity calculated is equal to percent %b. It will display 0 or 1 single bit value and it will take the value of parity reg. End always block end. So this is how function is declared and used inside the module.
Okay.
Just like a task, we can have multiple functions if required within a module.
Oh.
There are no limitations that you can have only one or two or three functions. You can have as many functions as you like inside the module.
Mhm.
But they all have to follow the rules for a function.
Yeah.
Okay, any questions?
No.
So we'll go forward. Yeah, this is mostly we had covered this. Yeah, so this is where actually we stopped last time. So we have seen that we should always use non-blocking assignments throughout our design for the reasons that
Mm.
we have discussed. And one of the rules in Verilog is, in case you are using blocking, you should never have a combination of blocking and non-blocking. If you're using blocking, then use blocking everywhere. If you're using non-blocking, use non-blocking everywhere. You cannot have non-blocking assignments for some signals and blocking assignment for other signals. So that's not allowed. And when you assign, don't make assignments to the same variable from more than one always block. Yeah, so this was an important digital concept. If you remember, we saw Verilog can potentially have four different logic values: logic 0, logic 1, x, which is an unknown value, and z, which is a tri-state value. So x is
Mhm.
getting generated, unknown value gets generated when you have a signal at any point of time should have only one driver. For example, if let's say there are two always block 1 and always block 2, and there is a signal called temp. Now temp is equal to, we are doing temp is equal to 0 in always block 1 and temp is equal to 1 in always block 2. Now any logic of always block 1 and logic of always block 2 will always work parallel with respect to each other, concurrently with respect to each other, or at the same time. That means we are going to assign 0 to temp and 1, logic 1 to temp and logic 0 to temp at the same time from always block 1 and always block 2. That is going to create problems for you in hardware because
Mhm.
then hardware won't know whether to assign a logic 0 to this signal or a logic 1 to this signal. That will generate an X value, the unknown value. And that is why you should not make assignments to the same variable or same signal from more than one always block.
Yeah.
Okay, don't make any assignment using hash 0 delays. So hash 0 or any hash values directly delays cannot be synthesized. I cannot ask the chip to wait for 5 minutes and do something. That doesn't work like that. So if you want to wait for 5 minutes and perform some logical operation inside the chip, you have to use the clock and generate a 5 minute timer. At the end of the 5 minute timer, you can execute some logic. But I cannot just say hash some value, wait for this much time, and then do something. It doesn't work like that in hardware. As so hash delays are anyway not synthesizable. So this is an example of one of the rules. This left hand side is using a blocking assignment, right hand side is using a non-blocking assignment. So we say non-blocking is the correct way to go. So always use non-blocking assignments.
Yep.
There are certain like simulation coding rules. We have some certain coding rules or design rules for synthesis when you're trying to describe Verilog for your design. Always keep in mind what sort of implementation your design could map to. If you don't know, chances a synthesis tool doesn't either. What this means is when you are the designer, you have a design specification given to you, and for that design specification, you're describing the design in Verilog, and ultimately that design will get converted to netlist format using the synthesis tool. So, for example, if you should know as a designer that first I want to create an adder. Let's say there are three signals A, B, and C, and C should get the result of A addition of A and B. So if you know this has to be implemented and you implement the adder correctly, only then A plus B will be implemented and C will get the result. So synthesis tool will also do it correctly. If you write some random Verilog logic and expect the synthesis tool to do perform certain miracles, it won't do that. Right? You have to describe the
Mm-hmm.
Verilog code correctly. Only then the job of the synthesis tool or the synthesis software is to convert your Verilog code to a gate level netlist format. It will not fix the errors in your design. The functional errors you have to take care of. On the functionality of the design, you have to be sure you're describing the logic correctly. If you describe the logic correctly in Verilog, synthesis tool will convert that logic to the required gates and netlist format. So you have to keep that in mind. Only allowed storage is instantiated D flip-flop, especially for FPGAs. There are a lot of flip-flops available in the library, but the only flip-flop that is available is the D flip-flop. We don't have other kinds of flip-flop available in the FPGA, like for example JK flip-flop or SR flip-flop or toggle flip-flops, which are part of digital logic design. They are part of
Mm-hmm.
digital logic design, but they are not. We cannot use them in for FPGA design purpose. Ultimately, FPGA design, the FPGA technology library, as we call it, only has D flip-flops in the library. So there are situations where you may want to instantiate that D flip-flop directly in your Verilog code. If you want to do that, you are free to do that. But you have to remember that the only type of flip-flop available is the D flip-flop, not any other flip. So okay, so then as far as possible, no loops, or wherever possible, you try to avoid loops or describe them in a very clear way. Many years ago, loops were not synthesizable. For loops, while loops were not synthesizable. Nowadays, all these loops are synthesizable. But at the same time, you should not make it very complex. That the synthesis tool will not understand how to do what they say unroll the loop. So if let's say you're doing a for loop for 10 times, 0 to 9, do something. It should be simple logic, done in a simple way where the synthesis tool understands how or what kind of logic you're trying to implement 10 times. For example, you can have a for loop for 10 for executing for 10 times. But inside the for loop, the logic should be very straightforward that the synthesis tool then understands that okay, this logic you want to replicate it 10 times. That's why you have included it in a loop. To make it as simple as possible. Again, going back to, I think you were not there during the digital logic section. See, Verilog is a language, I talked about this at that time. Verilog is a hardware description language. This language was
Mm-hmm.
invented for performing or designing hardware. Okay, people who come from a software background, from a programming background, their end goals are
Mm-hmm.
slightly different. Their program, their thinking process is different. The way they think is if you write small compact code, it is better most of the times. That's how a software
Mm-hmm.
programmer mentality is, coming from a programming background. For the
Mm-hmm.
hardware designer, this is a language which should be used to implement hardware. So end hardware that is going to get generated is the goal, and that hardware should be reliable and efficient. That's the goal. Having compact code is not the goal, or a few less number of lines of Verilog code is not going to make me happy as a hardware designer. If the end
Mm-hmm.
hardware that is generated, if that's efficient and that's reliable, it has to be consistent in its behavior. If it is reliable and consistent and efficient, then I am a happy hardware designer. Even though for that I need to write more Verilog lines, I'm okay with that. So typically
Yeah.
loops and other things are done to compact your code. Okay, so wherever possible, make it simple. So the synthesis tool doesn't make any mistake, and finally the hardware that you get is pretty consistent and efficient. Wherever possible,
Mhm.
avoid limit your arithmetic operators and other things. Or wherever you are, so you have to understand arithmetic operations, addition, subtractions, multiplication, division become a big bottleneck for designs when you're trying to work on very high speed design specifically. Or
Mhm.
sometimes you're the what we call congestion on a FPG or congestion on a device means my device the area of my chip I'm using 85 or 90 plus percent of my chip. That means it's a highly congested chip. A lot of logic area is used already. In such cases, if you try to implement arithmetic operators without thinking about, so you write your Verilog code thinking how this will get implemented. If you don't want certain arithmetic operators and other things, you should try to make your Verilog code efficient in that aspect. So that's
Mhm.
basically what it says. Use assign statements whenever possible. Assign statements are continuous assignments outside the always block. So when you use assign statements outside the always block, that is going to implement combinational logic for you. Combinational logic will be fast and it will not take much area. So that's good for design purpose. So use wherever possible, use assign statements. These are some of the rules. As you do more and more design, as you gain more experience, you will have your own rules and you will understand how to go about doing a design. But these are some of the rules you can follow while doing synthesis specifically. So yeah, so initially when we started out, initially when we started out logic synthesis, this was your behavioral Verilog code. Internally, there was an intermediate format called data flow format, and then it was converted to gate level. Nowadays, synthesis tool will directly go from behavioral to gate level. So this is your Verilog code. You synthesize the design, behavioral design of Verilog, and you directly gate level networks. Internally, there is a data flow part which is transparent to the user. The user doesn't see this. The user was able to see this many years ago, but nowadays you go from behavioral Verilog code to gate level synthesis netlist directly. That's the next step that you see. That's a code conversion method. See, these are some slides that we're going to look at synthesis. Synthesis is not part of this training program, but I just wanted to give you a brief idea. What are some of the problems you might face and some of the things, some of the guidelines you can follow. This particular training program will finish after we do the simulation aspect of the training. Okay. So we're going to learn
Okay.
the language, we're going to look at test bench design, we're going to look at simulation results, timing diagram generation, etc. But we will not focus on the synthesis aspect. We'll stop after simulation. But synthesis is
Mhm.
something that is very much part of the design, and a few slides on this topic will help you just get a feel for what synthesis does and what are some of the problems and maybe what you can do to avoid those kind of problems. So these are some slides based on the synthesis concept. Um, Combinational logic can be expressed as function of logical input. So output is always function of logical inputs. So there are some rules when you're trying to synthesize combinational logic. Try to avoid technology dependent modeling. What that means is when you describe your code, your design in Verilog, you should do that using purely the Verilog language that's available. You should not instantiate or directly use certain components from the technology library. So for example, if I'm developing a Verilog and let's say today I'm targeting a Xilinx FPGA, I know I'm going to target a Xilinx FPGA for my design. Even though I know I'm going to target a Xilinx FPGA for my design, my Verilog code should not directly include components from the Xilinx FPGA library. If I do that, my design becomes technology dependent. Means my design is locked to a Xilinx FPGA. That
Mhm.
Verilog is no longer portable. So I cannot take this Verilog as it is tomorrow and use an Intel FPGA, or day after tomorrow I cannot port it to a ASIC device. Why? Because my Verilog contains components specifically from the Xilinx FPGA library. That's why my design has become technology dependent on Xilinx. You don't want that to happen.
Mm-hmm.
So wherever possible, write Verilog, describe your design using Verilog purely language. Don't use the components directly in your design, if possible. If you do that, it becomes technology dependent. Combinational logic must not have feedbacks. If you have feedbacks, it will create loops. If you create loops, direct loops without proper logic inbuilt, then your design could go into a unknown state. It will go in a loop, or it will go in something called basically it will get locked somewhere. There is a chance it will get locked somewhere. So you do not want feedback, just direct feedback of combinational logic. Feedback, even there is a feedback, it should go through some other logic which can control the feedback. The feedback cannot be a direct feedback. Specify
Okay.
a output of a combinational behavior for all possible cases of inputs. So yeah, so let's say there is a combinational circuit that you have built using uh, different logic descriptions. So let's say there are five inputs and there is one output. So we have to decide what this point says is five inputs can have 2 raised to 5 combinations, 2 raised to 5 minus 1 combinations, for example. We should make sure that in all possible combination the output is clearly defined. If you don't define output for one of the combinations, the synthesis tool might assume something, and it will generate inefficient code, unreliable code that somehow the external factors are such that it goes into one of those unknown state, your output is undefined in that. So output should be defined for all possible combination of input sequence. That's one of the key things. Logic that
Mm-hmm.
is not combinational will be synthesized as sequential. So whatever combinational we have two kinds of circuits in digital design: sequential and combinational. So whatever is not combinational typically is sequential in nature. So
Mm-hmm.
sequential logic examples of flip flops, registers, counters, etc., memories, etc. And these rules are applicable not only for combinational but also for sequential logic. Some of these things.
Okay.
Synthesizable combinational logic can have following styles. It can be fully structural, so it can be netlist of gate instances. We have seen this kind of examples in earlier slides where we were taking a few gates. For example, we took two input NAND gates, two of them, and then we created a three input NAND gate at the start of the training. So we could
Uh-huh.
combinational logic can have a netlist of gate instances, or it can have something called combinational UDP. The UDP is a concept, it's slightly different concept. UDP, the full form is user defined primitives. What that means is the basic gates that we have in digital logic are AND gate, OR gate, XOR gate, etc. For some reason, you are not happy with the basic gates that are available in digital logic design. You want to design your own gate. You can call it my gate. And you want to define a truth table for that. So it's basically like you're designing a new gate altogether. It could be two inputs, three inputs, four inputs, whatever. If you design that gate and if you define truth table for it and you do all that things, customize things, it becomes a user defined primitive. So you are defining the primitive gate and you are defining the actions for what is the output for a given set of inputs. Such gates are called user defined primitives. Such user defined primitives are okay for simulation purpose, but they are not synthesizing.
Mm-hmm.
If you want to synthesize such logic, it is always good to develop a module, and for that module define the inputs outputs, and inside the module you can design a logic for a given set of inputs. So instead of doing a user defined gate, a user defined primitive, you can have your own module which then will become synthesizer. Okay.
Yeah.
Then functions can have combinational logic. Continuous assignment outside the always statement can have combinational logic. Behavioral statements also within the always block we can have combinational logic. Task which doesn't involve delays and events can implement combinational logic. Or we can have interconnected modules of the above. So any combination of the above. So this is what combinational logic, synthesize styles, and some of the important points are. You want to note any of this down? The synthesis part, this one or two slides.
Yes.
This one also.
Mm-hmm. Yep.
Okay.
I'm done with this.
Okay. Next slide.
I'm done with this.
Okay. Next slide.
I'm done with this one.
So these are some of the things that synthesis tool will do. Uh, this is a module that you see here. So pre-synthesis. So before synthesis, what you see here is there are four gates, out of which this gate, NAND gate, is a four input gate. Now after synthesis, the same logic. Now we're not going to details of it, but functionally it's the same logic. But if you see here, the gates are using only two inputs. The two input gates take less area, okay, compared to the four input gate here, what you see here. So the
Mhm.
synthesis tool will do some this is called logic optimization, that is done by the synthesis tool. So the functionality of the design will not change, it will remain the same, but here, since two input gates are used instead of four input gates, the overall area required will be lesser compared to pre-synthesis. This is called logic optimization, which is done by synthesis tool. Uh,
Okay.
So the way it works is the logic gates are internally translated to Boolean equations, and the Boolean equations are optimized. And then optimized Boolean equations are covered or implemented by library gates. So that is how synthesis will work. This logic will or this circuit will be first implement converted to Boolean equations. Then internally the synthesis tool will implement some kind of Boolean optimization techniques. You might have heard some of them like K-mass or Coin-McCliskey method or some other methods. There are multiple
Yeah.
optimization methods for digital logic. So synthesis tool uses some or all of them depending on what kind of tool you're using. And then it will come up with the optimized Boolean equation. And that optimized Boolean equation then will get implemented using this output circuit, not netlist. So this circuit gets, or this netlist gets converted to this, which is functionally the same, but it will take less number of gates or gates with less area. Same here, if you see here, this is a three input NAND gate. So this we got converted to all of them are two input gates now. Even though it took one gate additional here, but the three input gate takes more area, so two input gates take much lesser area. That's why it will prefer gates with two inputs. So we'll try to convert gates which has more than two inputs to two input gate circuits. This is just one type of optimization it performs. There are multiple optimizations the synthesis tool automatically does. You don't have to do anything. All you have to do is when you synthesize the design, you have two options. You say optimize for area or optimize for timing. If you say optimize for area, you will get a circuit with minimum area after synthesis. If you say optimize for timing, after synthesis you will get the fastest possible circuit, which has minimum delays. Okay, so that's how that works. We'll not go into details of that. So that is just something that to look forward to for synthesis if you do it sometime later.
Mhm.
Uh, Next important part of Verilog is we something called compiler directives. So what is that we see? A compiler directive may be used to control the compilation of a Verilog code or a Verilog description. The accent mark tick, we call it tick, denotes a compiler directive. Compiler directive, it is effective from the point at which it is declared to the point where some other directive overrides it, even across file boundaries. Across files also it remains the same. Compiler directives may appear anywhere in the source description of Verilog, but it is recommended that they appear outside a module declaration right at the top of the file. As in any language, each compiler has its own way of handling command line option. Compiler here means synthesis software, synthesis tool. For Verilog, the compiler is synthesis tool.
Mm-hmm.
Each compiler has its own way of handling command line options and supported compiler directives in code. Compilers may add additional compiler directives. They may not be portable and may not invoke the same actions. What this means is Verilog language supports certain standard compiler directives. Beyond that, every software will support its own additional set of compiler directives. So depending on which software you're using, it might support a few additional compiler directives that some other software may not support. But there are certain standard compiler directives which are part of Verilog language which are supported by all the synthesis tools. In that.
Okay.
For example, tick define, tick undefined. So tick include, if you don't C language programming is like hash include. If you want to include a header file, in C language you can include a header file or another C file. In this case, you can include some other file using the tick include compiler directive. Tick define uh, again is something like is like hash define but slightly different. In this case, you can define a macro with a macro code. So tick define, it's like a small section of Verilog code can be executed based on that definition. And tick undefined will undefine that macro code or macro name. We have certain um, examples of that. Tick if def, if tick else if, tick else and tick end if. It's like normal if else and if. The only difference is in this case, if a particular macro is like it can be a simple constant. So if you define a constant called say tick define my constant and the value is 1, for example. So we can say tick if def my constant. If the value is 1 means this will get satisfied. So anything between this and else tick else if, this number of lines will get executed. Tick else if we can have some other constant declared. So a typical example of this is in till a few years ago, we had two versions of Verilog code. One was which was synthesizable, and one which was only which could be used for simulation purpose. So there were always two versions of Verilog code, and those two versions used to vary slightly in certain sections. So what nowadays people do is we can use this macro or these labels called synthesis and simulation, for example. Tick if def synthesis. If synthesis macro is defined from this point till tick else if, all the in between lines would be used for synthesis purpose. That code. Tick else if simulation. So in that case, this particular section will be used for simulation. So we can control the type. So for simulation, which section of the code is used, for synthesis, which section of the code is used, can be controlled using this compiler directives, for example.
Okay.
Tick end def is not defined is the reverse of tick if def. If a particular macro is not defined, then execute something. Otherwise, do something else. Tick timescale is something that you're going to see very regularly. This is used a lot in test benches, not in design, but in test benches. So at the top of the test bench, you should always have a tick timescale defined. So how is it defined? Tick timescale 1 nanosecond / 1 nanosecond. So what this tells me is the first 1 nanosecond is my time units. So my time unit is nanoseconds. 1 nanosecond. So if I say hash 10, delay hash 10. So what's my time scale? 1 nanosecond. So hash 10 means 10 into 1 nanosecond means my delay is 10 nanoseconds in that case.
Mhm.
The second 1 nanosecond is the precision. Means for a simulation timing diagram, you can zoom in the timing diagram to see the details. How much you can zoom in is shown by this value. So
Okay.
the maximum zoom in is allowed is 1 nanosecond. So this is the minimum time period it will show in 1 nanosecond increments, not beyond that. I cannot go to picosecond level, for example.
Mm-hmm.
I have to wait. My simulation will not show details beyond 1 nanosecond. So that's a precision of your simulation or your time scale. First is a time unit, second is a precision. And tick time scale should be used at the top of the test bench whenever you're writing a test bench. You'll see that shortly. Okay, any questions here?
No.
So do you want to note any of this compiler directive stuff points for this?
Yes.
Okay.
I'm done with this.
Yeah. Next slide.
I'm done with this. I'm done with this.
Okay. Okay, system task will start next time onwards. Okay.
Okay.
So next class will be Friday, same time.
Okay.
Any questions on this section anywhere?
No questions on this. No.
Okay. Okay, have a good day. Yeah.
Thank you, you too.
Bye bye.